Sounds to which we normally listen, for instance over the telephone or over radio, must have been amplified hundreds of times before we can hear them. For example, the output of a microphone must be amplified before it can produce an audible sound through a loudspeaker. A device used to accomplish this is a vacuum tube amplifier, which increases low energy to a higher level in an identical wave form, or as nearly identical as possible. This energy is increased until the loudness or amplitude of the sound or speech heard is the same as that transmitted. Now let us examine a typical amplifier and, in general terms, see how this amplification is accomplished. If you speak into a microphone, the mechanical energy of sound waves is converted into electrical energy by the vibration of the diaphragm of the microphone under pressure of the sound waves. This vibration in a carbon microphone causes the diaphragm to first compress and then release the carbon granules in accordance with the pressure of the sound waves. This varies the resistance of the microphone element, which in turn causes more or less current to flow in the external circuit. The changing current in passing through the primary of a transformer sets up a changing magnetic field, which induces a voltage into the secondary. This electrical energy must be amplified before it can be reconverted into sound. We can then apply this energy to the grid of a vacuum tube and thus cause the current through the tube to vary in accordance with the voltage applied to the grid. The changing current flow through the tube can now be used to develop a much higher voltage across a plate load and either drive a speaker or another amplifier tube. Each of these steps causes a loss of a portion of the energy. We restore the lost energy by use of batteries and a vacuum tube amplifier. Now, in more specific terms, let's study the construction and operation of a typical voltage amplifier. The heart of this amplifier is the vacuum tube. Power for the output circuit is supplied by a B supply, in this case a battery. The positive side of the B battery is connected through a resistor to the plate of the tube. The negative side of the B battery is connected to the cathode. Bias voltage is supplied by a C battery with the positive side connected to the cathode and the negative side connected through a resistor to the grid. The output is taken across the plate resistor and the power supply. The input is applied across the grid resistor. When a small signal is applied to the grid, it varies the difference in potential between the grid and cathode. This causes the current flowing through the tube to vary in accordance with the difference in potential between the grid and cathode. This varying current flow through the tube causes the voltage across the plate load to decrease and increase. This voltage change across the output is an amplified reproduction of the input. It should be noted that the output voltage and the input voltage are 180 degrees out of phase with each other. Now suppose we place some values here. The B battery has a potential of 200 volts and the load resistor is 10,000 ohms. To compute E2, or the difference in potential between the plate and cathode, we must subtract E1 or the drop across the load resistor, from E3, or 200 volts. Therefore, we must first compute E1. Let's say that the bias is minus 9 volts, resulting in a static plate current of 6 milliamperes. The input signal has an amplitude of 1 volt. Using Ohm's law, we find that if we have 6 milliamperes of current flowing through a 10,000 ohm resistor, there is a 60 volt drop across the load. Subtract this 60 volts from the supply voltage of 200 volts, and we find that the difference in potential between the plate and cathode is 140 volts. When the positive portion of the signal reaches a peak of 1 volt, there is a difference of potential between grid and cathode of minus 8 volts. This is found by subtracting plus 1 volt from minus 9 volts. This reduction of the voltage difference between the grid and cathode allows more current to flow. If the current flow increases to 8 milliamperes, this causes the voltage across the load resistor to increase to 80 volts. The voltage between the plate and cathode will consequently decrease to 120 volts. When the signal voltage goes to a negative peak of minus 1 volt, the difference in potential between the grid and cathode becomes minus 10 volts, computed by adding minus 1 and minus 9. This increase in potential causes the current through the tube to decrease to 4 milliamperes. The voltage across the load resistor now decreases to 40 volts. And the plate to cathode voltage increases to 160 volts. Comparing the voltage change between the grid and the cathode to the voltage change between the plate and cathode, we find that there is a 2-volt change in the grid circuit. And a 40-volt change in the plate circuit. We have thus amplified the signal voltage 20 times. This amplified voltage is applied either to another stage of amplification, a loudspeaker, or some other device which uses the amplified output. It should be especially noted that the original signal influences only the current flow through the tube. And the plate voltage change becomes a new signal, which is an amplified reproduction of the input signal. The amount of bias placed on the tube determines its operating point. Practically every type of tube manufactured requires different plate voltages as well as bias voltages for particular modes of operation. A good tube manual will give the proper voltages for the condition under which the tube operates best. The saturation and cutoff voltages can be determined without a manual. A meter in the plate circuit will show how much current will flow when a fixed B+ voltage is applied. If we increase the plate voltage until a further increase makes no further change in plate current, the tube is then saturated. Applying a specific negative voltage on the grid decreases the plate current. This negative voltage is increased until the plate current meter reads 0. The tube is now cut off. The relationship between plate current, or IP, measured in milliamperes, and grid voltage, or EG, can be plotted on a graph. As a line is drawn from point to point, we derive a characteristic plate current curve. Note that we do not get a straight line, but a gradual movement upward until a point of saturation is reached. That portion of the curve which is straight is called the linear portion. If we apply the amount of bias which allows current to flow only within the linear portion, we are operating the tube as a linear amplifier, or as it is called, a Class A amplifier. In this type, the grid is most sensitive to a minute change in grid voltage. When operating a tube as a Class A amplifier, make sure that the signal voltage, shown here as the lower waveform, does not drive the tube beyond the limits of the linear portion of the curve. This will avoid distortion. If we bias the tube at or near cutoff, it is a Class B amplifier. Note that plate current represented by the upper waveform flows for only slightly more than 180 degrees of the input cycle. If we bias the tube between Class A and Class B, we have a Class AB amplifier. Again, note the relationship between plate current flow and the input cycle. If we bias the tube below cutoff, we have a Class C amplifier. This class of amplifier is almost exclusively limited to radio frequency applications. In a Class A amplifier, the plate current flows during the entire input cycle. This makes the Class A amplifier the least efficient, yet the most sensitive. As another example, in a Class C amplifier, plate current flows only during a portion of the positive half of the input signal and is cut off at all other times. The Class C amplifier is the least sensitive, but the most efficient. Amplifiers are also classified according to type of service, whether they are to be used as a voltage amplifier or a power amplifier. Most circuits contain several voltage amplifiers and one power amplifier. However, there are exceptions, especially in radio transmitters. A voltage amplifier is designed primarily to deliver a large varying output voltage to its load circuit. In order to accomplish this, there must be a relatively high value of load impedance. For a given vacuum tube voltage amplifier, the impedance of the load is usually as high or higher than the plate resistance of the tube. A tube manual will give the plate resistance for the tube selected and its recommended operating voltages. For voltage amplification, the most common choice of tubes is the pentode. There are 4 general methods for coupling the output of an amplifier stage to a following stage or to a load. They are resistance capacitance, impedance, transformer, and direct coupling. Each method has its own particular advantages and disadvantages, and therefore is employed in circuits where its advantages can best be put to use. Resistance capacitance, or RC coupled amplifiers, are so termed because the amplifier stages are coupled by combinations of resistances and capacitors. Advantages of RC coupled amplifiers are high fidelity over a wide range of frequencies, relatively high gain, low hum pickup from nearby AC fields, small space requirements, and low cost. The disadvantages of RC coupled amplifiers are higher B+ supply voltage is required and the reactance of the coupling capacitor increases at lower frequencies, thus reducing the gain. Now let's analyze a typical RC coupled pentode amplifier. In this schematic drawing, C1 is an input coupling capacitor from a previous stage. R1 is the grid return resistor which connects the grid to ground, or B-. It also develops the signal voltage for the tube. R2 is the cathode bias resistor, used to develop a voltage drop that can be used as bias for the tube. C2 is the cathode bypass capacitor, used here to filter out variations in the cathode current, thereby maintaining a constant drop across the cathode resistor. C4 is the screen bypass capacitor, which serves to remove any variation in screen current from the B+ voltage and to bypass these variations to ground. R5 is used as a screen dropping resistor. Its value depends upon the potential at which the screen must operate. R3 is the plate load resistor for the tube. Its value depends on the function of this amplifier and the type of tube used. The larger the value of the load, the lower the voltage on the plate. C3 is the output coupling capacitor for the tube and the input to the following stage. R4 is the second stage grid resistor and performs the same function as resistor R1. The RC coupled amplifier, because of its better frequency response, is used in almost all types of amplifier circuits where broad bands of frequencies are utilized, whether they be audio, RF, or even some UHF. Now let's change the plate load resistor to an inductor, and we have an impedance coupled, or LC, amplifier. LC amplifiers have one particular advantage. Removal of the plate load resistor reduces the voltage required from the power supply. However, LC amplifiers have a disadvantage. Due to the inductive reactance of the inductor at low frequencies, the gain is small. As the frequency is increased, the gain increases until the distributed capacitance of the circuit nullifies any further gain, and frequency response drops off. Therefore, around the middle of the audio frequency range, the LC amplifier will give maximum gain. Analysis of the circuit is essentially the same as for RC coupling. When it is desired to select one frequency out of the middle of the audio range, the inductor can be tuned by placing a capacitor across it. This makes the LC amplifier very selective. An amplifier circuit using transformers as coupling elements is called a transformer-coupled amplifier. This type may be used either as a voltage or power amplifier. When used as a voltage amplifier, transformer design can permit stepping up the voltage between amplifiers. One advantage of transformer coupling is that at lower frequencies, the step-up characteristics increase the voltage to a point where fewer amplifier stages are needed. When a transformer is used to couple between stages of amplification, it is called an interstage transformer. When the transformer is used in the final stage to couple the output to the device which will reproduce the sound, it is called an output transformer. Usually an output transformer has a step-down ratio because by reducing the output voltages, the current is increased to the larger values required by the load. It also serves to match the generally high impedance of the power amplifier to the commonly low impedance of the output device. Interstage transformer coupling is superior to other methods of interstage coupling in many respects. The step-up ratio permits the amplifier voltage gain to exceed the amplification factor of the tube. Transformer-coupled amplifiers can operate with a lower plate voltage. The circuit is readily adapted to push-pull operation. Transformer-coupled amplifiers have several disadvantages. The cost is greater, since the cost of transformers is considerably higher than RC coupling elements. Frequency response extends over a relatively narrow band and is less uniform than in other methods of coupling. Stray AC fields induce undesirable stray voltages into the transformer. Also, interstage transformer coupling requires an amplifier tube having a low plate resistance. To analyze the circuit, we can see that T1 and T2 are interstage transformers. T3 is an output transformer. When the microphone is energized, the very small voltage is stepped up through the interstage transformer and applied to the control grid of the first amplifier tube, V1. V1 is a standard pentode tube with the plate voltage being applied from the B+ supply through transformer T2. The bias for the tube is developed by the cathode resistor R1 and held constant by the bypass capacitor C1. The input signal influences the current flow through the tube, and this current, passing through the primary of the interstage transformer T2, induces a stepped-up voltage into the secondary. The same action is repeated for V2. But the voltage across transformer T3 is stepped down. When voltage is stepped down, current is stepped up, resulting in small voltage but high current across the speaker. As you know, power is equal to the current squared times the resistance. Thus, sufficient power is obtained to produce sound of the required loudness. Notice that in the plate circuit of V2, there is a resistor R5 and a capacitor C4. These elements are placed in the circuit to decouple any variation in the B+ voltage around the power supply. This type of circuit is found when there is more than one stage operated from the same power supply. In many RF circuits, tuned transformer coupling is used between stages. This method of coupling has several advantages. For one, it makes the circuit very selective. Still another advantage of tuned transformer coupling is that the bandwidth may be broadened by adding resistance to lower the Q of the tuned circuit. In addition, the cost of the transformers is substantially reduced. This is because there is no need for the iron core and the number of turns required is less. Now let's analyze a typical tuned transformer coupled circuit. Pentode tube V1 is operated as a Class A amplifier. This is determined by the cathode resistance and the fact that there is a very low DC resistance in the grid-to-cathode path. That is the secondary of T1. There are two reasons for operating the stage in this manner. One is that the grid will be more sensitive to any voltage change. And two, the tuned transformer makes the stage very selective. The screen voltage is applied through resistor R2. which drops enough voltage to supply the correct amount to the screen. Bypass capacitor C6 bypasses any variations in the screen current. The plate voltage is applied through the primary of T2. Ganged tuning capacitors C1, C2, C3, and C4 make resonance circuits of T1 and T2. All these circuits may be resonant at the same frequency or at different frequencies. A pentode tube is used in this circuit to give maximum gain to the signal voltage, which arrives at the antenna in the microvolt range. The last method we will discuss is direct coupling. A direct coupled amplifier, DC amplifier, is a vacuum tube circuit whose coupling network consists of resistive elements and direct connections. The chief difference between this method and RC coupling is the direct connection between the plate of V1 and the grid of V2, which eliminates the coupling capacitor used in RC coupling. Direct coupled amplifiers have several advantages. One, it has excellent low-frequency response. Another advantage is that the response of DC amplifiers is the same for slow variations as it is for non-varying signals. And a direct coupled amplifier is suitable for amplifying both alternating and direct current signals. Chief disadvantage of DC amplifiers is that due to distributed capacity in the circuit, the response drops off in the high frequency range. Direct coupled amplifier circuits are used chiefly in vacuum tube voltmeters, in oscilloscope deflection amplifiers, and in radio teletype circuits. To review some of the main points, a vacuum tube amplifier amplifies sound by increasing low-level energy to a higher level in an identical waveform or as nearly identical as possible. There is a particular use and mode of operation for Class A amplifiers, Class B amplifiers, Class AB amplifiers, and Class C amplifiers. Amplifiers are also classified according to types of service, whether they are to be used as a voltage amplifier or a power amplifier. There are 4 general methods of interstage coupling. They are resistance-capacitance coupling, impedance coupling, transformer coupling, and direct coupling. It is important that you learn the theory and operation of basic amplifiers. That you know their classes and types, advantages, disadvantages, and use. That you become thoroughly familiar with methods of coupling and multi-stage operation. It is only by a thorough understanding of all this and more that you may become an expert in the increasingly vital field of electronic equipment repair.